All right, Honors Chem, we are now going to talk about strong bases. Now, in the last video, we learned that strong acids were able to ionize 100% of the time. Strong bases are pretty much the same thing, but because bases are made with metals and hydroxide ions, notice we are using the Arrhenius definition of bases. They're already ions. They're not covalently bound. So instead of using the word ionization, we're going to use the word dissociate because the ions just dissociate in water from each other. They break apart. Okay? So here we go. Bases. What you have read about acids can be applied to bases, except instead of producing hydrogen ions, we're going to produce hydroxide ions. Okay, for example, the conductivity of a base also depends on the extent which the base produces hydroxide ions. So we still need to have ions in solution for that base to conduct electricity. And strong bases will conduct a lot of electricity because we will have a lot of ions in solution. A base that dissociates entirely into metal ions and hydroxide ions is known as a strong base. So we need it to dissociate or break from the ions that are held together in a salt into individual ions in the water. And it's going to dissociate into metal ions and hydroxide ions. Those are strong bases that dissociate entirely. Okay? So it needs to be 100% dissociation. Therefore, some metallic hydroxides, such as sodium hydroxide, are strong bases. Notice we have a one-way directional arrow. Sodium and hydroxide will make the sodium ion and the hydroxide ion in an aqueous solution. It is dissolvable. Now, if you remember back to our solubility rules, what was our rule with hydroxides? Think about that for a second. Okay, so here we go. Dissociation constants or equations for strong bases. We have sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. So what was our rule? All hydroxides were soluble if they were 1A or group 1 metal. So the strong bases are group 1 metal hydroxides. So if you remember, group 1 metals is that very first column of the periodic table. So if I look at that first column, let's get our periodic table up. If we get that periodic table up, we should have this whole first group. Lithium, sodium, potassium, rubidium, and cesium hydroxide. I'm not going to go all the way down to francium because francium, let's be honest, is so radioactive that you really can't get it. Its half-life is just 22.5 minutes. Okay? So, our group 1 hydroxides are all going to be strong. They're all going to be strong because they are all soluble. So, that means we will have sodium hydroxide, potassium hydroxide. Let me go down the list. Oop, I forgot lithium. Lithium hydroxide, cesium hydroxide, and rubidium hydroxide. Because those are all the group metals and they are all soluble. And if you remember, we also had group 2 metals that were exceptions. Those were calcium, barium, and strontium. So we have a couple that are group 2 metals. We have calcium hydroxide, we have strontium hydroxide, and we have barium hydroxide. Okay, those were also the soluble ones. And they will dissociate fairly well as well. Group 1s dissociate or they dissociate a little bit better than the group 2, but both of them will create a lot of ions and dissociate very well and conduct electricity very well. So these need to be learned just like your strong acids. Now, in contrast to strong bases, weak bases, just like weak acids, only ionize partially. So they also have an equilibrium going on. They only ionize partially, and because of that, they only produce very dilute solutions. For example, methylamine reacts with water to produce an equilibrium between methylamine molecules, methylamine molecules, and hydroxide ions. So notice the methylamine acts as an acid. It pulls a water hydrogen off. Okay? And because of it, it leaves the OH ion as an ion in solution. Now, we can use this as, actually it doesn't, this, if I remember correctly, this is labeled completely wrong. So the water is actually acting as an acid. The methylamide is reacting as the base. Okay? So here we go. And it's really useful to draw the Lewis structure here to see what's going on, I think. We have a lone pair here. And that lone pair here is what attracts that H from the water. Okay? So that lone pair is attracting that H from the water. So when we have the conjugate acid, we will have the methyl triamine with the lone pair with the hydrogen bound to it there. And then the hydroxide is what's left from the water. Okay? So notice also another thing about this. Did you notice this reaction arrow? That reaction arrow is wrong as well. This reaction arrow should be a double-headed arrow. So it is going both ways. Weak bases produce an equilibrium just like weak acids, where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay? And because of that rate being the same, we never get to completion. So that reaction never goes all the way. We always have some of the products, we always have some of the reactants, and it never ionizes completely. Okay? So you need to learn your weak acids, your strong bases, and your weak base, and your strong bases. Now it's a lot easier to learn your strong acids and your strong bases and memorize those and realize that everything else is weak. Okay, so that's where I'm starting, and I put a little video to help you memorize your strong bases or your strong acids on there. Just remember your strong bases are the only hydroxides that are soluble, if you remember your solubility rules. Okay, all right, now we're going to start on our next video. We are going to talk about why this dissociation constant of these acids and bases get into how we deal with water as well. All right, so we'll see you next time. Have a great day. Bye.